Hello, this is our dissection by Andrew, Mehali, Hunter, and Joon. We dissected a Vornado humidifier and fan. The way that the system works is shown here. The wick filter absorbs the water in the basin of the humidifier. Dry air from the air intake blows through the porous media and allows for the moisture to evaporate and get propelled into the room through the help of the fan.
This analysis on the fan can be inaccurate as there is an induced magnetic field from the DC motor which causes a spike in the anemometer reading. However, to work around this, we used a piece of paper and held it in front of our humidifier, then tried to recreate the bend on the paper with a larger fan and measure the anemometer, the speed. We were able to treat the system like an actuator, assuming velocity right before and after the fan were the same, which is approximately 4.4 meters per second. Now in the air outlet area, we can get the flow rate to be 0.0674 meters cubed per second. In addition, using the equations provided in the textbook, the pressure right before the actuator is PATM minus 1/2 rho U rotor squared. And according to online specifications, the RPM of the rotor is approximately 1,250 RPM in low speed. Knowing that fan radius, we can calculate velocity of the rotor using V is equal to omega times R. Also, the pressure right after the actuators is P18 plus 3/2 times U rotor squared. So, finding the difference between the pressure right before and after the actuators gives us a change in pressure of 204 PA.
The wick is a mesh of shredded material. Inside each strand, water travels through tiny pores, which we have estimated to have a diameter of 6 micrometers. The flow through the wick can be described using capillary action and Poiseuille flow, which is a laminar flow through a pipe due to pressure gradients. The water and air interface creates surface tension, which causes the water to stick to the pore surface. From the diagram, you can see the contact angle the water makes with the surface. Since we estimated the wick material to be paper, we know that the contact angle will be around 30 degrees. Contact angles below 90 degrees cause concave upstruct curvature of the liquid, which creates a pressure difference where the water side pressure is lower than the atmospheric pressure. To analyze the flow through the wick, we use the Washburn equation to find the time for the water to reach the top of the wick, which is about 5 minutes. Within a long pipe, the constant pressure difference will have a lower pressure gradient. To find the change in pressure across the curved interface, which is what drives the fluid through the pore, we use the Young-Laplace equation to get a pressure drop of around 41,000 PA, since a lot of pressure will be needed to get the fluid through a small hole. Using that and the change in height, we were able to find the Poiseuille flow velocity distribution, flow rate, the mean velocity, Reynolds number, and the viscous dissipation factor.
We also estimated the number of pores in the entire wick to be 120,000 to find the total flow rate throughout the wick, but it is extremely small. The velocity and time calculations are also relatively not good if you would expect your humidifier to work instantly. However, 5 minutes is not a terrible time. Additionally, the Reynolds number indicates that we are approaching creep flow and microfluids territory, which makes sense if you're looking at one pore. In creep flow, the fluid is non-turbulent and the viscous forces overpowers. Our viscous dissipation factor for one channel is 0.0246, which is low, but if you look at the system as 120,000 pores, viscous losses dominate.
As for the fan, our values of specific speed and diameter fall in the region of low pressure and high flow rate of a specific speed versus specific diameter graph, which validates our calculations as this is somewhat expected from an axial flow pump.
If we decrease the fan diameter to be smaller, we get values for our specific speed and specific diameter to fall closer to the upper left-hand corner of this graph, which is the region of a good axial flow pump. The Reynolds number calculated for the fan is high, showing that it is in turbulent flow. This makes sense because it not only changes the direction of flow by 90 degrees, but its flow through the wick causes disruptions. Turbulent flow and low pressure change is expected out of a humidifier because the humid air is misting throughout the room, which is a larger area.
Overall, our wick system has a somewhat slow flow where viscous forces dominate and the specific speed/specific diameter are not exactly what you want it to be for an axial flow pump. We would not recommend the Vornado humidifier as many other people also don't in Amazon reviews.